Okay, good morning. So welcome to our first online lecture. And last time we talked about quotient groups and about fundamental homomorphism fundamental homomorphism theorem. So this lecture can be basically called like first applications of quotient groups. And fundamental homomorphism theorem. Fundamental homomorphism. Sorry, it still takes some time to get used to this pen. Probably move it. Homomorphism theorem. So this lecture is planned to consist of 4 distinct topics. Oh, no. So in the first part, we will talk about the fact that the converse to Lagrangian, the converse to the theorem of Lagrange is false. Converse to theorem of Lagrange is false. Is false. Now in the second part, we will talk about the basic facts of quotient groups. Facts about quotient groups. While in the third part, we will talk about simple groups. Simple groups. And if time permits, so this lecture was originally planned for the Blackboard talk. I'm not sure that I can write with the pen as fast as I do on the Blackboard. So the fourth part will be about center subgroups and commutator subgroups. Commutator subgroups. Now, feel free to ask questions at any moment. Just unmute your sound and ask questions. Okay, so let's get started with the first part. So I will save the Blackboard. I will clear. Unfortunately, I haven't figured out the way how to show you the previous Blackboards. One. Converse to Lagrange theorem is false. Okay, so before we prove the following, so let's recall from previous lectures. That if we have a finite group, so the first statement is Lagrange's theorem. So let H be a subgroup of G, of a finite group G, be a subgroup of a finite group G, then what we know for sure is that the order of H and the order of H divides the order of G. The order of G. Note that this theorem itself doesn't say anything about the existence of a subgroup of an order which divides of a given order which is a divisor of G. So the only thing it says that if H is a subgroup, then the order must divide the order of a group. However, we haven't seen any examples, of certain order of a finite group for which we cannot find the subgroup yet. And the reason for that is because if G is abelian, and it's crucial here, and finite, then what the fundamental theorem of finitely generated abelian groups implies. So then fundamental theorem on finitely generated abelian groups plus theorem 6.14 in the textbook, which tells us about the structure of subgroups of a cyclic groups, subgroups of a cyclic group. So altogether, they would imply that for every n, which divides the order of G, there exists a subgroup of this order. There exists H in G such that the number of elements in the subgroup equals to n. However, as I mentioned, abelian here is crucial, and in general, the converse to the Lagrange theorem is false. However, converse to Lagrange theorem is false in general. Examples exist for non-abelian groups. Or better say counterexamples. Counterexamples. Okay, so let's save this blackboard. And the first counterexample we are going to talk about today, okay, so saved, let's clear, will be the following. Counterexample 1. So we will consider an alternating group A4. So the order of A4 is exactly the order of the symmetric group on 4 letters divided by 2. So that's 4 factorial divided by 2. That's 12, right? And we will prove the following claim. So naively, you would expect that there might exist a subgroups of orders 2, 3, 4, 6, well, 1 and 12, of course. And what we claim is that A4 has no subgroup of order 6, of order 6. Okay, and the proof would go as follows. Oh, first of all, let me pause, and if you have any questions about the previous slides or the formulation of examples, please unmute and ask questions.
Hello?
Yes?
I was just wondering what theorem 6.14 states again.
So the theorem 6.14 basically says that if you have a cyclic group, right, then and you have an order, right, then you take any divisor and you would find a subgroup of an appropriate order.
Okay.
So
thank you.
basically, you take the appropriate. You take the divisor, right? You take if you have. Should I go back? If someone wants me to go back, please say so. I'll go back on the and comment on 6.14.
Yeah.
But
do you mind?
Okay.
Thank you.
Let me. Okay. So
Sorry about that.
No, that's great. That's thanks. So let G be a cyclic group generated by A, be a finite cyclic group. And let's say that the order of G equals to n capital. Okay, so consider any D, any natural number D, which divides n. Then there exists a subgroup H of our cyclic group such that the order of H equals to D. And the proof here would go as follows. And the proof here would go as follows. So kind of what as a set, what is G? So it's a to the 0, a to the 1, and all the way to a to the n minus 1, right?
Mm-hmm.
So G, the set is a to the 0, all the way to n minus 1. Now take B to be a to the following power, n divided by d. That's not, let me write it this way, n divided by d. So because d is a divisor, n divided by d is a natural number, right?
Mm-hmm.
So then what will be a cyclic group generated by b? So it will be, of course, b to the 0, right? B to the 1, all the way to b to the d minus 1. Because b to the d will be exactly a to the n. B to the d equals a to the n equals to e, right? So then the cyclic group generated by b has exactly d elements.
Okay.
That's the proof. So you know this for a cyclic group, and you know that any finite abelian group is a product of cyclic groups, right? So it's not that hard to conclude from here that this would mean that for any divisor of an order of a finite abelian group, you can find a subgroup with that order. So is it clear? Please.
No, this makes sense. Thank you.
Okay. Okay, but the crucial here, was that, okay, so here for this lemma, the crucial part was that this was a cyclic group. And in the kind of bullet on the previous slide, the crucial was that we consider a finite abelian group. Now, if we look at non-abelian group, this doesn't work out anymore. And this is the simplest counterexample you can find. So, any more questions so far? Okay, so let's go ahead and prove this counterexample. And kind of the key part of the proof will be the use of quotient groups. So in general, it's much simpler to prove that that a group has a subgroup of a given order, right? You just present this subgroup. Now, how would you prove that kind of large subgroup don't have a large group like A4 don't have a subgroup of order 6, right? There is no chance we can examine all possible subgroups of order 6, or all possible subsets of order 6 and prove that each one is not a subgroup. That's basically impossible. There's just too many of them. Okay, so for the proof, we will go as follows. Let's suppose there exists such a subgroup. Suppose there exists H in A4 such that order of H equals to 6. Okay, so now, as you might see, 6 is exactly half of the 12. So then there exists exactly two left cosets of H in A4. All right? Namely, one coset will be the coset containing an identity, EH, that's the H itself. And the second coset will be the coset containing any element which is not in H. So this will be one coset, and this will be another coset. A4 minus H. So basically everything which is not in H must be in the other coset of H. So here, let me put cross-reference to recall last problem from midterm 1. Now there's something very special about a subgroup which has exactly two cosets. And this can be formulated as follows. So we know that left cosets are H and everything which is not in H. Now similarly, there exists exactly two right cosets. Cosets of H in A4. And this is, of course, the coset containing an identity that's H. And that's A4 minus H. That will be the other cosets. Now, in particular, the left and right cosets coincide. So if we look at this, left and right cosets of H coincide. In other words, H is normal subgroup. Here we go. Okay, so let's save this slide. And before I move on to the next slide, any questions so far? Okay, now it's clear. Now, the claim, as you might guess, is that, okay, claim H is normal. Let's put it here. Is normal. Should I repeat how to prove? Anyway, so that's. So now, because H is normal, we can define the quotient group. We can define the quotient group. A4 mod H. Oh, so let me write it on the next line. So we can define the quotient group A4 mod H, which will consist of left cosets of H. So one will be E times H, and the other will be sigma times H. So here, sigma is any element in A4 minus H. Just take any element from A4 minus H, then it will be in the other coset. Okay, and define the quotient group. And this is a group with two elements.
Professor?
Yes?
So in this case, just making sure, in this case, sigma represents more than one possible permutation, right?
It's enough to take any. So that's a good question. Thank you. So what we proved on the previous slide is that there exists exactly two left cosets of H and A. One is H, and the other is A4 minus H. Now you can take any element in A4 minus H and consider a coset sigma times H. And because there is only one coset containing, because this is A4 minus H is exactly the coset containing sigma, that will be the same thing for all possible choices of sigma there. Is it clear?
So each of those terms is a distinct coset.
No. Every sigma in A4 minus H gives sigma times H, gives the coset containing sigma precisely A4 minus H.
Okay.
So that's might be a good exercise to write this down explicitly for a few different sigmas in well, I mean, there is no such H, so that will be the main statement of our lecture. Anyway, so of course, all elements which are not in H, the coset containing them will be A4 minus H. So that's provided that H exists. We actually will prove that such H of order 6 cannot exist. Okay, so now the number of elements in A4 mod H equals to 2. So this is a group with two elements. And there's actually only one group with two elements. So A4 mod H must be isomorphic to Z2. Must be isomorphic to a cyclic group with two elements. In particular, what this would mean if we look at the cosets containing sigma. So let's look at sigma times h, right? And let's look at sigma. Let's look at the product of these two cosets. Now, as we defined on the previous lecture, since we proved that h is normal, it must be true that this is the same as the coset containing sigma squared, right, times h. But on the other hand, because it's the multiplication, it's like 1 plus 1 in Z2, that should be the same as the identity of the quotient group, namely the coset containing identity. So in other words, sigma squared must be in our normal subgroup H. And note that we actually proved that this is true for all sigma in A4 minus H. No matter which sigma from A4 minus H you take, then the square of this guy must be in your normal subgroup. So what we can now do, we can examine several cases of permutations in alternating groups and show that there's actually a kind of too many elements which must be in H. So let me save this blackboard and let's clear it.
Professor?
Yes?
Really quickly, how did we get that sigma squared h is equal to E times h?
Okay, thank you. And that's a good question. Let me go back. Now, what we there exists only one group which contains two elements, and that's Z2, right? So what's the multiplication table in Z2? So Z2. So we have two elements, 0 and 1, right? 0 and 1. And the multiplication table looks as follows, 0, 1, 1, 0, right? Now, on the other hand, if we look at A4 mod H and look at the multiplication table, so there is two elements. One element is the coset containing an identity. The other element is the coset containing sigma, right? And because this is a group, it must be isomorphic to Z2. So in other words, what we will find in this multiplication table is EH, sigma H, EH. And that's exactly what we're using here. So sigma H is EH.
Okay, thank you.
Yeah. On the other hand, we know that sigma H star sigma H is the same as the coset containing sigma squared. So the cosets containing identity and sigma squared are the same, which precisely means that sigma squared is contained in our normal subgroup H. Thank you, that was a good question. So that's the best place to make this remark. Any more questions so far? Okay, so now let's prove that there must be too many elements in H, more than 6 at least. Okay, so let's save this blackboard. Let's clear it. Okay, so now let's examine all cycles of order 3. Okay, so what do we have? For example, we have cycle which cyclically permutes 1, 2, and 3. That of course belongs to A4. Then if we take the square of this guy, 1, 2, 3 squared, that's 1, 2, 3 composed with 1, 2, 3. Okay, so in terms of the 2-row notation. So 1 goes to 2, 2 goes to 3, right? 2 goes to 3, 3 goes to 1. 3 goes to 1, 1 goes to 2, and 4 stays the same, right? So this is the cycle, 1, 3, 2. And because the square of every element in A4 minus H must belong to H, sure enough, the square of all element of a subgroup must belong to the subgroup, so the result must be in H, right? Now, similar argument would work for another element, 1, 3, 2 in A4. Now, 1, 3, 2, if we compute the square, we will obtain that this is 1, 2, 3. And again, it must be in our subgroup H. Now, similarly, we get that 1, 2, 4 is in H. 1, 4, 2 must be in H. 1, 3, 4 must be in H. 1, 4, 3 must be in H. And of course, 2, 3, well, so we excluded 3, so 1, 3, 4, 1, 4, 3, 2, 3, 4, and 2, 4, 3. Now, as you may see, there's just too many elements that must be in H. And of course, the trivial permutation must be in H. So there is at least there is at least 9 elements in H, which contradicts our initial assumptions, which contradicts our initial assumption that the order of a subgroup H equals to 6, which means that there cannot exist a subgroup of order 6. So that concludes the proof of the lemma. So any questions so far?
Professor?
Mm-hmm.
So all of this that we just did was to demonstrate that if you have a given order, there doesn't have to exist a subgroup with that order if it divides the...
Exactly.
Okay, and so you use the example of A4 to demonstrate that?
Yes, that's the simplest possible example where you, where there for order 6, for example, there doesn't exist a subgroup. Of course, as the subgroups got bigger, there are more and more examples, but here you can see it very easily.
But it is true for abelian groups though, right?
Yes, it is true for finite abelian groups. And that has to do with structure of subgroups of cyclic group and the fact that any finite abelian group is essentially a product of cyclic groups.
Okay.
So,
okay, thank you.
Yes. Any more questions?
Where did we use the property that H is a normal subgroup in doing this? Why didn't we just go ahead and show like this slide in the first step initially?
Awesome question. So it was important for us to define the quotient group. Remember, now let me see if I can open the slides. 10. Here we go. Whiteboard. Oh, sorry. Yeah, unfortunately, I didn't find a good way to scroll between the slides, but it was important for us to define the quotient group. So remember, you were asking how did we conclude that sigma h times sigma h is the coset containing identity. So for this, it was essential that we used an isomorphism with a cyclic group of order 2. And in order to talk about the isomorphism with a cyclic group of order 2, on the first place, you have to prove that the cosets of H do form a group, that you can talk about the quotient group. And for this, you need H to be normal. Does it clarify the question?
Yeah, I think so.
Okay, thank you. That's okay. So that was the first part of our lecture. So we used quotient groups. Quotient groups to show that the converse to Lagrange theorem is false. Okay, so let's move on to the second part. So in the second part, we will talk about some basic facts. Where's the? Oh. Basic facts about quotient groups. About quotient groups.
Professor?
Yes.
I have a quick question about how this pertains to linear algebra.
Mm-hmm.
So I'm taking 110 right now, and the professor was talking about also quotient groups, but with respect to affine subsets. Is an affine subset just the analog of a coset for abstract algebra?
That's true. Well, I mean, we gave an example of particular affine subsets, which are linear subspaces, right? And those are in particular, those are subgroups. But because vector space is a abelian group, every subgroup is normal. So you can talk about the quotient. And this would really coincide with the fact. Now, what is crucially different in the abstract algebra from the linear algebra is that we talk about not necessarily abelian groups. We also talk about non-abelian groups. And here the story becomes different. We have to worry whether the subgroup is normal, and a lot of the techniques and proofs, they are much different. So, but this is a particular example, of course, of a quotient group when you have affine subspace, which is actually a linear space.
Okay, thank you.
Not every affine subspace is linear space, but okay. Okay, so the first theorem we're going to prove is, so we have product of groups and we have quotient of groups. And these two are related with each other by the following theorem. So that will be our theorem 1 today. So let G be H cross K be direct product of groups, be direct product of groups. Now then, the first thing is that the subgroup H bar, which is the subgroup consisting of an elements HE, such that H is an H and E is an identity in K. So let's say that's E sub K. Is a normal subgroup, is a normal subgroup. And second of all, so whenever we have a normal subgroup, we can take a quotient by that, and this quotient will be isomorphic to K. In other words, if you take group H, right, and take a direct product with a group K, and then take a quotient by this H, you will get K. So, and for this proof, kind of this proof will be neat and short because it will essentially use the fundamental homomorphism theorem. So for the proof, we will do the following. So first of all, we will look at the projection map. Okay. First of all, we will look at the projection map from the group G to the group K. So this projection map does the following thing. So element of a group G is a pair, H small, K small, right? And what it does, it just forgets everything about H. So it sends it to K. Okay, so this map is a group homomorphism. Is a group homomorphism. And you can see it. You can see it explicitly. So let's take pi2 of the product. So let's take pi2 of H1 K1 multiplied by H2 K2. Okay, so this is pi2 of the pair H1 H2 K1 K2. This is how the product in the direct product of groups works. Well, and if you take the second component of that, you will get just K1 K2. And that's exactly if you just take the second components of H1 K1 and of H2 K2 and multiply them together. H2 K2. So this is a group homomorphism. And what you can conclude from here is that the kernel of this group homomorphism is exactly H bar. Note that kernel of pi2, so this is basically the subset HK, such that pi2 of HK, which is just pi2 of HK, which is K equal to E. And this is exactly H bar. Kernel is a normal subgroup. So H bar is a normal subgroup. Here we go. And now for the second part, and probably here I would have to go to the next slide. And before I do that, any questions? Any questions about the formulations or the proof so far of the first bullet? Okay, so let's clear everything and let's go to the second bullet. Now, for the second bullet, let's recall the fundamental homomorphism theorem. So suppose we have a group G, and we have a homomorphism, and we have a homomorphism pi2 to some other group K. So we have a quotient of this. We have a quotient of this, and that's we have a quotient of G by a normal subgroup, which is the kernel of pi2, which is H bar. So there's a gamma there, right? And there is a group homomorphism mu here. So by fundamental homomorphism theorem, we know that the image of pi2 is the same as the quotient G by H bar. A fundamental homomorphism theorem we know that G mod H bar is isomorphic to the image of pi2. And in this case, the image coincides with the entire K, because this homomorphism is obviously surjective. So let me just put this comment here. That's because pi 2 is onto. Of course, pi 2 of G is entire K. Okay, so that concludes the proof of the second part of the theorem. Here we go. So, any questions so far? Now, the interesting thing, yes?
I'm just wondering, will you post, like, in the future, like, would you post these slides
Oh, yeah,
after
of
lecture?
course. I will combine them to the PDF and I'll upload to vCourses. So, yeah.
Okay, thank you.
You're welcome. Okay, so now the interesting thing about this theorem is that it works only one way. Exactly as it's stated. Okay, so remark. Let me put this in red. Mark. That the above theorem works only one way. And I'll explain what that means in the next two examples. Okay. Oh. Example 2. So if we start with a group Z6, right, and we already proved that it's isomorphic. It's isomorphic to Z2 cross Z3. Z2 cross Z3. And if we look at the quotient over Z6, over Z6 by, let's take Z2. So in Z6, there is a subgroup of order 2, which is isomorphic to Z2. Then it will be isomorphic to Z3. However, and that's why you have to apply this theorem only exactly as it's stated. If you take group Z4, now in the Z4, there is a subgroup isomorphic to Z2. There is a subgroup isomorphic to Z2. And if you take a quotient of that, you will find that the resulting group is a group of two elements. It's isomorphic to Z2. But Z4 itself is not isomorphic to Z2 cross Z2. So that's the comment that if you have the direct product of the two groups on the first place, then of course quotienting by the subgroup H bar, gives you just one of the other groups in the product. But it doesn't work in the reverse direction. That if you know the right-hand side, that you can conclude that the result is just a direct product. So this has to do with something which is normally the topic of a second course in abstract algebra, which is called the semi-direct product. So if time permits, we will say a few words about this in the end, but so far let's just move on to the next theorem. Before I move on to the next theorem, any questions? Let me save the Blackboard. Okay. So now the second basic property of the quotient subgroups has to do with cyclic groups. So theorem 2, a quotient group, let's better say any quotient group of a cyclic group, any quotient group, cyclic group is cyclic. Okay, so here the proof would be basically by finding a generator of the quotient group. So let G be a cyclic group and N be a subgroup of G. And be a subgroup of G. Well, because cyclic groups are always abelian, this subgroup, because cyclic groups are abelian and is a normal subgroup. Well, subgroup. So we can consider the quotient group. And we can consider the quotient group G mod N. Okay, so now the claim is the following, that the coset AN, so remember that the quotient group as a set, it consists of cosets. So this is E, N, etc. Other left cosets. So claim that AN, that's an element of the quotient group, generates G mod N. Okay, so let's see how the proof goes. So what happens if we multiply these two cosets in the quotient group? So as a result, we will get a coset containing a squared, right? Now, similarly, you can conclude that if you take AN and raise it to the power k, this is the same as the coset containing AK. But now, because all elements, now because G is cyclic, because G is cyclic, all elements of G are all elements of G are of the form a to the k, are of the form a to the k for some k. As a result, all cosets are of the form a to the k. Now I ran out of slides. I ran out of slide and I really want to write it here. All cosets are of the form coset containing AK. Here we go. So this means that if you look at all powers of A, then you will span all possible cosets. Now, of course, different powers of A might still give you the same coset, but that's precisely because the order of a quotient group will be smaller than the order of the original group in general. But basically what you have is that you can get all possible cosets in this way. Okay, so any questions about that? me save this blackboard. Okay, and now let's move on to the third part of our lecture. So in the third part, we will talk about simple groups. Simple groups. And we will start by giving a definition of what it means to be a simple group. And that'll be definition 1. So a group is called simple if it has no proper non-trivial normal subgroups. If yes,
is this part 3 or 4?
Oh, it's part 3. Yeah. Thanks. Let's write it carefully. So a group is called simple if it contains no proper non-trivial normal subgroups. These no proper non-trivial normal subgroups. Okay, so we actually already know an example of that. Example that will be example 4, I believe. That Z sub P for prime P for prime P is simple. Now here the reason is immediate, right? ZP has no proper non-trivial subgroups at all. Now there is a slightly more elaborate example. If you look at the alternating group AN for n greater or equal than 5, it is also simple. And that's actually the main reason why this alternating group have its own name. Why it's important to look at the subgroup generated by even containing even permutations. Now, the proof of that will be left as homework. And instead we will formulate the following theorem. So that'll be theorem 3. So there's a nice interplay between the homomorphism and I mean, there's a nice interplay between the group homomorphisms and normal subgroups, as you might guess, which is coming from the fundamental homomorphism theorem. So the theorem 3 would have two parts, and it is formulated as follows. So let phi from G to G prime be a group homomorphism. Oh, actually, let me go to the next slide, because I don't want to break the statement of the theorem. So I'll save, clear everything. Theorem 3. I'll let phi be a group homomorphism from G to G prime. G to G prime. Be a group homomorphism. Now, the first statement we're going to prove is that the image, well, we're not going to prove that, so it'll be left as homework as well. But the first part of the theorem is that the image of a normal subgroup is normal. group is normal. And the second part is that the pre-image of a normal subgroup is normal. Normal subgroup is normal. Okay, so proof will be one of the homework exercises. So the point is that under the group homomorphisms, the normal subgroups behaves naturally. So that's the main meaning of this term. So earlier we proved that kind of the image of a subgroup is a subgroup and the pre-image of a subgroup is a subgroup. Now, if among all subgroups you would look only at normal subgroups, the similar statement is true. Okay. And in particular, what will be interesting is a relation between simple groups and the so-called maximal normal subgroups. So we will use this theorem 3 to talk about maximal normal subgroups, but before, let's make a definition. And that'll be definition 2. We say that n in G is a maximal normal subgroup if the following holds. That first of all, n is a proper normal subgroup. Proper normal subgroup. Now we have to exclude this case when n equals g, right? It's a boring. So it must be a proper normal subgroup. And second of all, there exists no larger proper normal subgroup. Or if we formulate it precisely, there exists no proper normal subgroup n prime in G such that n prime is strictly greater than n, and at the same time it is strictly less than G. So there exists no other proper normal subgroups in between n and G. Now the key thing here I want to stress out is that it is a maximal normal subgroups. In other words, maximal normal subgroup is not unique. So let me, okay, so we saved it, let's clear it. We make a remark. A maximal normal subgroup is not unique in general, is not unique in general, and you can see it on a very simple example. So let's look at G. Let's look at the G, which is the direct product of Z2 cross Z3. That's isomorphic to Z6. Now both Z2 cross E, that's a subgroup of G, and E cross Z3, that's a subgroup of G, are maximal normal subgroups. Are maximal normal subgroups. Okay, so why maximal normal subgroups are interesting though? And they're interesting because of the following theorem. That's theorem 4. So M in G is a maximal normal subgroup, is a maximal normal subgroup if and only if and only if the corresponding quotient group G mod M is simple. Yes?
Why is Z2 cross E maximal?
Because if you add, so here's the point. If you add any other element, let's say, I don't know, A, B, right, in G. And this B would be non-identity.
Okay.
Let me actually. Indeed. Suppose there is a bigger, suppose there exists n prime in between these two groups, in Z2 cross E, n prime and less than G. So take an element AB in n prime minus Z2 cross E, right?
Okay.
So this would mean that B cannot be equal to an identity, right?
Okay, because otherwise it would be in Z2 cross E, right?
Yeah.
Okay.
But then, because A0 belongs to Z2 cross E, right?
Mm-hmm.
This would imply that 0B belongs to n prime. And because every non-zero element is a generator in Z3, this would mean that E cross Z3 is a subset of n prime in particular. So
Okay.
you would generate everything. So you would generate the entire thing. And prime really, well, let's shorten this. Let's shorten this to the conclusion that n prime must be equal to G.
Okay.
Because altogether 1, 0, and 0B generate the entire thing. 1, 0, and 0B generate the entire G. And same reasoning for the other case. So if you take at least one element from G which is not in E cross Z3, then together with E cross Z3, they will generate the entire G.
Okay.
There are simply no subgroups in between. Okay, so any more questions? Okay, so now let's go ahead and prove this theorem. So let's start with a direct implication. And suppose there exists, oh, wait a second. M prime, maximal number subgroup, if and only if. Wait a second, that's an opposite implication. Okay, so suppose there exists a subgroup in between M prime, such that it's in between M and G, then what do we have? So we would have that, okay, so this is our G, and this is a group homomorphism to G mod M, which is gamma from the previous lecture. So if we have subgroup M prime of G, right, then under this homomorphism gamma, it will be sent to a group M prime over G, which is a subgroup of G mod M. So this is gamma of M prime. Now what we have here is that this is a proper normal subgroup of G mod M. Okay, so if we know that G mod M is simple, then this is impossible. Possible if G mod M is simple. Okay, so this is what we now proved, is that if G mod M is simple, this implies that M in G is a maximal subgroup. Okay, so let's save this slide. Now let's move on to the other part, which will be the direct implication. Actually, we will prove the following. So we will prove that if G mod M is not simple, suppose that G mod M is not simple, well, then there must exist a subgroup. There exists a subgroup, let's call it N prime in G mod M, which is a proper normal subgroup. Well, and let's take the preimage M, the preimage of this subgroup under the Okay, so first let's look at the preimage of the identity of this gamma, and that will be M. And in between M and G, we will find another subgroup, which is M prime, which is the preimage of our N prime, gamma inverse of N prime in G. So M is not a maximal normal subgroup. Here we go. And that together with the first part implies that M is a maximal normal subgroup if and only if the quotient is simple. Okay, so why do we care? So any questions about the theorems so far? Okay, so why do we care about, that will be probably a good place to conclude the lecture. So why do we care about the simple groups at all? So you remember that when we talked about the finitely generated abelian groups, we were able to describe all of them by the so-called fundamental theorem of finitely generated abelian groups, right? So we proved that every finitely generated abelian groups is just a product of cyclic groups. Now, things get complicated when you move, things get more complicated when you move to non-abelian groups. You cannot just use direct product to construct all of them. That's not true. But in a sense, this simple groups, they serve as the basic building blocks of finite groups in general. And in particular, there exists a classification theorem. So that's slightly beyond the scope of the course, but let's let me give you a bird's eye view of what we're doing here. So remark on importance of simple groups. So moral, simple groups serve as building blocks of finite groups. And here it's important to say that that we have to use the so-called semi-direct product to build any finite group. And in particular, there exists a classification theorem for these building blocks. Now there exists a theorem, and the proof of this theorem, that's hilarious, is over 10,000 pages long. And I'm not joking right now. Over 10,000 pages long proof. Sure enough, we won't talk about the proof of this theorem in this class. That every finite simple group is isomorphic to one of the following groups. Yes, isomorphic to the one of the following groups. Okay, so the first example we already seen, and that was ZP, cyclic groups of prime order, cyclic groups of prime order. The other case is the alternating group for n greater or equal than 5. Alternating group. Now there is the so-called groups of Lie type. Groups of Lie type. And there are 27 exceptional groups called sporadic. So these are all infinite series, right? So there are infinitely many primes, there are infinitely many alternating groups. Same goes for the groups of Lie type. There are infinite series of groups. And there are 27 exceptional groups, one of the 27 exceptional groups called sporadic. Null groups called sporadic. And now in some complicated way, you can construct out of these 4 types of groups, you can construct any finite group. But this goes slightly beyond what we will be discussing in this course. Anyway, so I'll stop here, and if you have any questions, please feel free to ask. I will continue office hours with the same meeting ID, but I will restart. The meeting just to keep the recording of the video separately. So from the lecture, yes.
Thank you, Professor.
Yes. Okay, so.
So, Professor?
Yes, just let's restart the meeting for the office hours.
Okay, but I just have a simple question.
Okay, I mean, go ahead. That's, yeah.
Thank you. So you said there are 27 exceptional groups called sporadic, right?
Yes.
But actually, I found on the Wikipedia that it says that there are only 26 exceptional
Oh, that's
groups.
an excellent question. So there is actually the so-called TITS group. So sometimes it's called sporadic as well. So 27 is like 26 plus 1.
Oh, really?
Yeah. So on the Wikipedia there is if you open there will be another case, like 5th case. And the reason is that this one probably was missed when they first did the classification.
Oh, okay. Thank you.
So, welcome.